Hey, good day, good people. Let us look at the second part of heat, of compound bar, I mean to say. The first part we were dealing with the combination of two materials, be it copper and combined with steel. We call them compound bar. We looked at the expansion, the material changing in length due to the applied force. But the second part of it deals with the expansion of material due to heat. Now, we know that when heat is being transferred to any material, that material it will experience the change in length. Now, in calculating the change in length as a result of heat, this is the formula that we are using. Change in length equals to length original multiplied by alpha. Alpha it is the coefficient of expansion multiplied by change in temperature. Now, this is the formula that we are using to calculate the change in length as a result of heat being transferred to this combination there or any material, not only this combination, but to any material. Now, then in calculating the change in length, in temperature, it is change in temperature equals to T2 minus T1. Now, but when coming to this byproduct, the change in temperature, be careful. If you are given words like rises by, ne, then you know that the given temperature, it is the byproduct. Or if they use words like increases by, then you know that the given temperature, it is the byproduct. But if you are given words like temperature increases from, ne, increases from 2, then you know that surely you are given T1 increases from T1 to T2. Then you need to apply this formula. Change in temperature equals to T2 minus T1. Now, please, when coming to temperature, be careful. Right. Now, this is the formula that we'll be using to calculate the change in temperature. Then in calculating the final length, it is the change in the change in length plus length original, then you are able to get what? The final length. Right. This is the formula. This is one of the formulas that we'll be working with in calculating the change in temperature as a result of what? Of heat. Now, let's look at this concept a bit. Let's look at this concept a bit. Now, we are given those two materials and the heat it's been unleashed on this combination here. Now, copper, what is it that we know about copper? Copper, it is of soft material. It means copper, it will respond quicker comparing to what? To steel, because steel, it is of hard material. Now, when heat it's been transferred on this combination, you'd realize that copper, it will expand quicker, or rather it will respond quicker to what? To the transferred energy. Then steel, it will expand slowly. So why? It is of hard material. It is hard. It is not easy to dismantle the molecule so that this can expand as freely as it wants. Ne? Now, you would realize that as a result of steel being hard, now steel, it's the level of what? Of expansion. Now, steel controls to which level must this combination do what? Expand. If steel expands to this level, if steel expands to this level, it means copper as well. It needs to come back to the level of what? To the level of steel. Because now steel, it is the measuring stick of expansion of this combination here. Now you realize that steel, it is heading one way. It's experiencing a tensile expansion or a tensile force. Then copper, at first, as it was responding to the transference of energy, it was experiencing tensile, you can tell. But because of steel, it's a measuring stick. Steel will try to pull copper to its level. Now you'd realize, therefore, that when copper it is coming back to the level of steel, copper it is now experiencing the force compression, while steel is experiencing what? The force tensile. Now you can tell that there's this force that causes the material to experience what? Stress. Now that force, it causes this two material to push or to pull. Now that's the force that we need to calculate in calculating the stress that takes place in this combination of the two. Now in this case, under the expansion due to heat, you'd realize that F1 equals to F2. Then we know that the change in length 1 equals to the change in length 2. They have or they must expand to the same level because they are combined, they are joined together. Now we know that the change in length 1 equals to the change in length 2. That we know. How do we then calculate the change in length? Don't forget that in calculating the change in length, it is change in length LO coefficient multiplied by change in temperature. But the force that takes place in the combination of the two, that's the one that causes this expansion in this material. Now we know that if that's the case, change in length copper equals to change in length steel. Now we are having change in length copper equals to the change in length steel. Then we are having LO change in the coefficient of expansion copper multiplied by the change in temperature minus the change as a result of what? Of that force here. This one, it has to do with what? With the expansion as a result of or responding to the transference of energy. Then this one, it is caused by that force here, F1 equals to F2. It causes the stress in the material. It causes the change in the material. Then we are having equals to, based on this given information there, LO coefficient of steel multiplied by the change in temperature plus XS. This is the change steel, that is the change copper. We've written it as X minus and X. This indicates to you that of hard material it must always be written as plus. Then of soft material it must be written as what? As minus. Because tensile it is the addition. Then compressive it is what? The minus. You can tell that copper is experiencing what? Compression. Now hence it is minus. Then this one, it is of hard material. It's experiencing one way root. It is plus. That is why it is force tensile. It is plus. Right. That is why we are having this formula here. Now, we will then say LO coefficient copper, change in temperature steel. Then we'll transpose this to the left hand side. Then it will be minus LO coefficient of steel multiplied by change in temperature equals to, then we'll transpose this one to the right hand side, then it will be XC plus XS. That's what we will have then. Right. Then here we know that L1, the conditions, L1 equals to L2. Now the L and the L, they are equal, they will fall out. Then here I'm left with change in temperature as my common factor equals to coefficient of expansion copper minus the coefficient of expansion steel equals to, what is the formula of calculating the change as a result of force? It is FL over AE. Then here I'm having force. Force, it is common. It is this force here, the pulling or the pushing, that force there. It is force common equals to area copper Now let's make a dot there. Area copper over length. That should be length copper. Let's wipe the whole thing there. It is force common multiplied by L copper over area copper multiplied by Young modulus copper plus F common multiplied by L steel divide by area steel multiplied by Young modulus steel. Then we know that L and L, the fact that we said they are equal, L and L, they will do what? They will fall out. Then we will have force as our common factor. Then we are having force as our common factor, 1 over AE. This is your copper plus 1 over AE steel equals to change in temperature, open bracket, coefficient of copper minus. This is what we have. This is the formula that we will be using under the change, under the expansion due to what? Due to heat. This is the formula that we'll be using here. This is the formula. This is the parallel formula. Please, parallel formula. You can tell that the condition that we dealt with here, they have to do with what? With parallel. You can tell. Now, those that of series connection, we are having, for series connection, yes, we are having F1 equals to F2 as well, because it is that force that causes the pulling and the pushing. That's what we have there. Then we are having the change 1 equals to the change 2. That's what we have under your series connection. Then we are having LO, coefficient of copper, multiplied by the change in temperature minus the change in copper as a result of force equals to the change in steel as a result of force plus LO, coefficient of steel, multiplied by the change in temperature. Then when we transpose LO, copper, change in temperature, transposing this one to that side, it will be, remember here it's a minus. It's not supposed to be a plus there, it's supposed to be a minus. Here it's a minus, right? The change, it is positive. The coefficient there, it is positive to indicate that it is of hard material, it's experiencing tensile. Now, this one, it is negative because it experiences what? Compressive. Now, it will be, when we transpose that to the other side, it will be plus LO, change in steel coefficient, then it will be XS plus XC. Then here, the only thing which is common, it will be the change in temperature. But the length, they are not of the same. If you are given a diagram like this, you'd find that the material, it is not of same length. You are having copper, you are having steel. They are not of same length. The length of copper, L1, it is not the same as what of steel. Now, hence, this won't be common. This it will be length copper, this will be length steel. Not unless they are of the same length. Now, if they are not of the same length, then we are having the change in temperature as a common factor. Then we are having LO, coefficient of expansion, plus LO, coefficient of what? Of expansion for steel. You can either work it out this way, or you can work it out in that manner there. It doesn't matter. Now, let's work with what you have in your books. LO, coefficient, change in temperature, plus LO, coefficient of steel, change in temperature, equals to FL over AE, copper, plus FL over AE steel. Now this is L for steel, L for copper. If they are not of the same length, now they can't fall out if they are of the same length. But force there, it is common. Then we are having F open bracket LC over A EC plus LS over AS. That's what we have there. LO, coefficient copper, change in temperature, plus LO, coefficient steel, change in temp. This is the formula that we have. But if they are of the same length, then you will be having change in temperature, open bracket, coefficient copper plus coefficient steel equals to F open bracket 1 over AE copper plus 1 over AE steel. If this one, it's an if question. If length it is equal, then this is appropriate. Now, this is the formula of the expansion of material due to what? Due to heat under your series connection. This is the formula that we'll be using to calculate whatever that they want us to calculate under your series connection. Now, we'll be working with those two formulas in calculating the change. Now, if you were to be asked to calculate the change or the final length of those material, compounded material, if you'll be asked to calculate the change in length of those compounded material. Now you are having, as a result of heat, you are having change equals to LO, coefficient of expansion, change in temperature. If it is of copper, it will be minus. Then the change in length, if it is of steel, it will be LO, steel, change in temperature plus XS. You will be using these formulas to calculate the change. Then you take the values of those formulas, then you calculate LF equals to the change. This one, it is the copper, that one, it is the steel. Change in steel plus L original, then you get the L final. Whenever you are questioned and they want you to calculate the change in length thereafter, these are the two formulas that you need to calculate in calculating that change. After you've calculated that and that, then you apply that formula to calculate the change. When they want you to calculate the final, then this is the formula for final change. Under heat. Don't forget that this is under heat. Change under what? Under heat, the transference of energy. Now we'll be working with those formulas. Then I will post the applications of the formulas that we spoke about. Thank you, good people.